Welcome back to Vibe Podcast. Today we're discussing a comparison of Jane Wallentine's passport numbers and the 1970 Isdal Woman's fake passport numbers, a topic researched for us by David Morgan. I'm joined by Charles and Angela.
Hello everyone, Charles here, a criminology expert. I'm always keen to look at cold cases, but I tend to be a bit wary of getting too lost in the numbers when we're talking about real people and real crimes.
And I'm Angela, a mathematician. I'm absolutely thrilled to delve into this topic because it's a fantastic example of how advanced statistical analysis can shed light on seemingly impossible connections. I'm already buzzing about the data.
Excellent. So, let's dive straight in. David Morgan's research revisits the curious case of Jane Wallentine, who appeared in 1970 police evidence concerning the Isdal Woman. There are some striking similarities already. She was staying in a hostel in Stavanger when the Isdal Woman was in the St. Svithin Hotel, bought the same boots from the same shop, and had 2 suitcases identical to the Isdal Woman's. She also travelled by hydrofoil to Bergen and then apparently sent a postcard from Sweden dated the 27th of November 1970. Just 2 days before the body was found in the Isdalen. What's even more intriguing is that no one ever checked whether she was alive after 1970. But the core of David's analysis, and what we're discussing today, focuses on her passport number, A155 blah blah blah, I'm keeping it secret, and the various fake passport numbers used by the Isdal Woman. Angela, the initial analysis found a 75% digit match rate between Wallentine's passport and the Isdal Woman's fake passports, compared to an expected random match rate of 60%. That 15 percentage point difference sounds significant, doesn't it?
Absolutely, Alice. It's incredibly exciting. A 15 percentage point difference immediately suggests something more than just random chance. It points towards a potential deliberate construction, a pattern that shouldn't exist if these numbers were truly random. This is where the numbers start to tell a story.
Hold on a minute, Angela. Deliberate construction. We're talking about a few digits here. A 15% difference, while it sounds nice on paper, doesn't automatically scream smoking gun to me. Coincidences happen all the time, especially when you're looking for them. We need more than just a gut feeling about percentages. What kind of rigorous analysis are we talking about here?
That's a fair question, Charles, and that's precisely why we employ advanced techniques. The document outlines several statistical methods to move beyond just an initial observation. For instance, we used a chi-square goodness of fit test.
And what does that tell us, Angela?
Well, the chi-square test helps us determine if the observed digit distribution significantly differs from what we'd expect if the digits were randomly generated. We observed 27 matches out of 36 digits, where random chance would predict about 21.6 matches. We calculated a chi-square value of 3.38.
And, does that mean anything concrete?
The critical value for statistical significance at a 0.05 level is 3.84. Our 3.38 value is slightly below that. So, technically, we cannot quite reject the null hypothesis that it's random at that conventional 0.05 level. However, the p-value is approximately 0.066. This means there's only about a 6.6% probability of observing this level of deviation by random chance alone. It's incredibly close to being statistically significant and definitely warrants deeper investigation.
Not quite reject the null hypothesis. So, essentially, the numbers aren't definitively telling us anything, are they? It's still in the realm of, could be random. I'm not convinced we're making a breakthrough here if the first big test comes back with a, maybe.
But that's just the first step, Charles. We then move to a more precise approach, binomial probability analysis. This calculates the exact probability of observing 27 or more matches out of 36 trials, given a 60% probability for each individual match. And the result? The probability of obtaining 27 or more successes is approximately 0.0789.
So, a 7.9% chance of this happening randomly.
Precisely, Alice. That's quite a low probability. While it still doesn't meet the conventional 0.05 threshold for statistical significance, it's certainly not a high chance. It suggests the pattern is not entirely random. We're talking about a relatively rare event if it were purely coincidental.
7.9%. Angela, that's roughly a 1 in 13 chance. I wouldn't call that impossible. People win the lottery with much lower odds. If you're going to tell me these passport numbers are deliberately linked, I need something with much more certainty than a 1 in 13 chance. That's still a significant amount of wiggle room for randomness, in my book.
And that's why we bring in the big guns, Charles, Monte Carlo simulation. To really establish robust empirical confidence intervals, we simulated 10,000 random sequences of 36 digits, each with a 60% probability of matching Wallentine's digits. And guess what? Approximately 7.9% of these sequences contain 27 or more matches, which is consistent with our binomial calculation.
So, essentially, you're running the scenario thousands of times to see how often this match rate would occur by chance.
Exactly. And what this tells us is that our observed 75% match rate places us above the 92nd percentile of the distribution. It's like finding a unique snowflake in a snowstorm, but we know statistically how rare that snowflake is. It's not impossible by chance, no, but it is relatively uncommon. A visualization of this would show our 75% match rate sitting way out in the right tail of the bell curve, far from the expected 60%. This provides a much more intuitive understanding of how unusual this match rate really is.
So, what you're saying is, if we roll the dice 10,000 times, our outcome would still appear about 790 times. That's still a lot of times for something to be considered uncommon, but not impossible. I appreciate the number crunching, Angela, but in criminology, we look for something more definitive. Tangible connections, not just a high percentile of unusualness in a statistical model.
But Charles, when direct evidence is scarce, these advanced analytical techniques can be invaluable. They quantify our suspicions, providing a measurable probability that this isn't just a coincidence. It doesn't definitively prove a link, but it provides powerful statistical support that this pattern is likely deliberate. It guides our understanding and points towards a potential connection that is statistically unlikely to be random.
It truly is fascinating how mathematics can illuminate these cold cases. It seems we have a strong statistical suggestion of a non-random connection, even if it doesn't meet the absolute highest bar of conventional statistical significance. It certainly makes you wonder about Jane Wallentine's true identity and relationship to the Isdal Woman.
I'm still not convinced it's not a coincidence, but the fact she was following the trail of the Isdal Woman should have been followed up by the Norwegian police. I mean, there is such a thing as female killers. I might just knock on that door in Seattle to see whether Jane's still alive in her 80s.
Interesting, Charles. That's all for today. A big thank you to our guest researcher, David Morgan, for once again providing our topic.